Good afternoon everyone. So we are going to continue with the special class sessions of mechanics. This is part 2. Okay. So yesterday we had quite a bit of a discussion about first of all the state of stress at a point, and then we discussed a number of things, among which one very important concept we discussed near the end was about the transformation of stresses. So we discussed about transforming from sigma xx, sigma yy, tau xy to sigma x dash and x dash. We also talked about how to obtain the expression for tau x dash, y dash, and finally we obtained the expression for sigma y dash and y dash. All right. So going forward, what we will do is we'll talk about transformation of stresses in that spirit, but one very special version of the transformation of stresses, which is usually referred to as principal stresses. So the first topic of discussion today is principal stresses. Very closely connected to the concept of principal stresses will be another topic called maximum shear stresses. So we will discuss that also. So let's see how much we can finish in this first hour, after which we'll take a short break and then continue as required. All right. First of all, regarding this principal stresses, what we are going to do is carry forward the expressions that we had obtained yesterday on the expressions of sigma x dash, sigma y dash, and tau x dash, y dash, and see what we can do with it. In fact, for our purposes today, we will not need directly the expression of sigma y dash. So effectively what we need is the equation number 3 and the equation number 4 that we had obtained yesterday. All right. Please note that the first of these equations we had numbered as equation 3, and this one we had numbered as equation 4 yesterday. So these equation numbers are from yesterday. I believe the technical people from the Center for Educational Technology will provide the links in this video for that lecture also. So now what we are going to do, a little bit of a manipulation. So you see, I can easily transpose this part, the sigma xx plus sigma yy by 2, to the left hand side. Now if I do that and do a little bit of an algebraic manipulation, I can obtain something very, very insightful. So what I will do is, I will transpose this to the left hand side. All right. I will name this as my equation 3 dash, just to distinguish it from the previous version, and then what I will do is I will square this equation number 3 dash, square this equation, and then I will also square this equation number 4 and see what I can obtain. So, this is the plan. So, that gets squared. What I will also obtain is this thing squared. Okay. So, on the right hand side what I should obtain is sigma xx minus sigma yy by 2 cos 2 theta plus tau xy sin 2 theta, the whole square of that, that is the whole square, and then this entire thing is also whole squared. We do not have to number this intermediate equation. All right. Now, all that I have to do is just do a little bit of algebraic simplification on the right hand side. You see, these two terms, I will obtain a sigma xx minus sigma yy by 2 whole square from that, but very nicely I am going to obtain a cos square 2 theta and a sin square 2 theta. So, together that will just reduce very nicely. So, instead of discussing this orally, let me quickly obtain the expression. I may have to reduce the font size of my writing a little bit to adjust within the limited space of this board. So, that is just writing out the expanding the first square on the right hand side, and then if I expand the square on the second term, now the last one that I am missing here is just the sigma xx minus sigma yy by 2 multiplied by tau xy cos 2 theta. It is important to note that we should not be forgetting this minus sign. Okay. Sorry. There should be a sin 2 theta also. Thank you. Okay. Now, you can see very easily that this term here, it cancels perfectly with this term. So, overall what I will have is this term combining with this term to give me just this sigma xx minus sigma yy by 2 whole square. Similarly, this tau xy square, because there is a sin square 2 theta, it can be combined very nicely with this cos square 2 theta term. So, overall what I am going to get at the end of my algebraic simplification is just this. Alright. Now, what have we gained by doing all these algebraic manipulations? Well, you see, this is looking somewhat familiar to me from whatever notions we have developed from our studies of coordinate geometry. You see, suppose I imagine that this is like a x, suppose I imagine that this is like a y, then this is like x minus something whole square plus y square is equal to something on the right hand side. So, very faintly I can write like this, that this is something like x minus a whole square plus y square plus r square. This is what I want to imagine this entire equation to be written as. If we do that, then very quickly I realize that even though these are representations of something physical, some stress representations, but somehow they have managed to come out in the form of a circle. So, if they are really looking like a circle in terms of algebra, can we perhaps draw this circle and gain some more insights into it? Answer is yes, of course, and we will exactly do that. Okay. So, to make the writing easier on the board, I will reduce my font size significantly and just repeat this entire equation in somewhat shorter. Okay. What I will do is, I will write this as sigma average, and it really makes sense because you can see that this is some sort of an average of the sigma xx and the sigma yy, the two normal stresses that we have in our reduced two-dimensional plane stress situation. So, this is our sigma average. What we will do here is, we will call this as r square, r denoting some sort of a radius. Now, let us actually draw this diagram. As I had mentioned earlier, my plan is to treat this sigma x dash as my x and my tau x dash y dash as my y. So, in that spirit, let me draw this circle. Now, when I draw this circle, you may think whether it should be centered here or should it be centered here, should it be centered here. Well, I do not know, because right now, because I am not actually doing any particular problem, I do not have in my hand any particular value of this sigma xx and sigma yy. When we do certain problems later on, we will see that it will actually make some concrete sense. Right now, we will keep this as general as possible. So, it does not really hurt us if we consider that perhaps this entire value is something positive, so that we might as well consider the center to be on the right hand side of the origin, and we will draw a circle here. So, believe it or not, this is supposed to be a perfect circle, okay. So, please assume that this is a perfect circle, okay. So, this is sigma average, and the radius of this circle, we understand that this is like this, alright. Now, directly from this picture, we can obtain a number of, yes, so, directly from this diagram we can obtain a number of insights. So, first of all, you see that this circle is cutting the x axis, which is the sigma x dash axis at 2 points. Now, this is one of these points, this is another point. So, we will call this A, this we will call as B, and the center one we will call as C. Okay. Now, you see, when I am sitting on this point A or I am sitting on this point B, I am actually addressing a very special situation. What is that special situation? You see, this is my sigma x dash axis, but if you consider this tau x dash y dash axis, the value of tau x dash y dash at A or at B, it is equal to 0. So, I emphasize once more that at A or at B, the value of tau x dash y dash is equal to 0. Now, this is a very special situation. Why? You see, if you consider this entire circle and you consider the various possible values of the sigma x dash that are possible on this circle, as long as you stay on this circle, what is the maximum possible value of this sigma x dash? Is this here? Is this here? Is this here? Is this here? Or is it perhaps here? The answer, of course, is that if we really consider the maximum possible value of sigma x dash, it is here. Similarly, the minimum possible value of sigma x dash is here. So, we have two new insights here. First of all is that at A and B, we have tau x dash y dash to be 0, and very specially, whenever such a thing is occurring that tau x dash y dash is equal to 0, we also have that sigma x dash is taking on the maximum value here and it is taking on the minimum value here. So, together we can say that A and B represent the extreme values of sigma x dash. Alright. So, in terms of expressions, how does this new insight help us in going forward? So, we will keep this diagram as it is and maybe go on to that side to obtain some expressions. So, first of all, you note when tau x dash y dash is equal to 0, what do we have? Well, one quick thing which we can check is what happens if we actually go to the expression of tau x dash y dash. So, let us write that down quickly. So, tau x dash y dash was this thing. So, basically what I have done here is to rewrite equation number 4 from earlier. Now, we are considering this very special situation, which means that this is equal to 0. If that is so, then can I not write from this expression directly that tan to theta is equal to all right. Now, you all understand that this is a very special case of this angle theta. So, what are we doing? We are considering the special case that tau x dash y dash is equal to 0. All of this discussion pertains to these 2 points A and B. Now, you note that the very topic of our discussion was named as principal stresses. So, what are these principal stresses? The sigma x dash and the sigma x dash values that we have at A and B, these are basically referred to as the principal stresses. So, you can think of it in 2 ways. First of all is that wherever you have the tau x dash y dash to be equal to 0, you can say that you have the principal values of your normal stresses there, or you can equivalently say that the maximum values of the normal stresses wherever they are, those are the principal values. Okay. Because this is such a special scenario we are considering, what we should be doing is, instead of keeping on writing like this general theta, we should be naming it in a very special way. So, we name this as tan 2 theta p. The p subscript here denotes that we are referring to the angle theta as it pertains to the principal stresses. Mind you, we are talking about principal stresses. Alright. Now you see, suppose we are actually doing a particular problem, and at a particular point we have certain values of this tau xy, sigma xx and sigma yy as it is referred to a particular set of coordinate axes. Now, using your calculator, you can certainly find out this value of theta p, but we also know from our high school geometry that if a certain value of twice theta p is satisfying this equation, then twice theta p plus 180 degrees should also be satisfying this very same equation. Now, if that is so, we can actually write this down very neatly, that so let's go here. Effectively, what we are saying here is that to solve this equation, you have two choices of theta p. So, both of these are valid solutions. If that is so, can we not equivalently write that our valid solutions are theta p and theta p plus 90 degrees? So, theta p is one solution, equivalently theta p plus 90 degree is also a solution which is going to satisfy that equation. Now, what does all of that mean? Before we can actually go into an interpretation of the meaning of these angles, you note that it was absolutely necessary that we obtained two different values from this equation. Why? Because you see, when we are considering this particular thing, we do not only want to obtain one principal stress at A, rather we want principal stress at both A and B. Then surely the two solutions that we are obtaining here, that is theta p and theta p plus 90 degree, must somehow pertain to A and B. Only one of them is not going to give us the correct answer. Okay, so we understand that much, that theta p and theta p plus 90 degree must pertain to A and B. Now, does it really make sense with whatever we were discussing? So, if you forget about this particular circle for one moment and just think about the diagrams that we were considering yesterday. So, yesterday we were repeatedly considering this kind of a square stress element, and what we said was that this pertained to a particular reference axis or coordinate axis like x and y, and we considered a rotated coordinate system x dash and y dash, and corresponding to that we had our square in this fashion. Sorry, this is a horrible picture. Okay, somewhat better. So the white one here, the straight white one, that one corresponds to x and y, and this tilted one, the blue one, it corresponds to x dash and y dash. And we said that this angle was theta. Now what we are discussing today is a special value of that theta in terms of this theta p. So what we are saying is that maybe when we are considering this kind of a tilt, at that particular value of the tilt, the tau x dash y dash is coming out to be equal to be 0, and at that particular situation we have this special value of sigma x dash x dash. But we are also simultaneously obtaining the theta p plus 90 degree. Where is that theta p plus 90 degree? Now if you look here carefully, if this is theta, then this one, the y dash is tilted to x at theta plus 90 degrees. So if we are considering our special case of theta p, this particular plane, this tilted top plane, this one, that is actually inclined to this one at theta p plus 90 degree. So the values of the normal stresses that we are obtaining, the sigma x dash, that is giving us an answer for sigma x dash itself, as well as it is giving us an answer for sigma y dash. Before we go into more details about that, let us look about something insightful regarding the maximum value of the shear stress. So here in this, coming back to this diagram, you see that this is our tau x dash y dash, which is the shear stress. Okay. So just like previously we were considering various possible values of sigma x dash, this time we are not going to bother about the normal stress, we are going to bother ourselves with this. Now as you move along this circle, you sit at various points on the periphery of this circle and you note down the various values of this tau x dash y dash. Where on this circle will you obtain the maximum possible magnitudes? Mark my words carefully. Where on this circle will you obtain the maximum possible magnitudes of this tau x dash y dash? Is it here? Is it here? Is it here? Is it here? Where? Certainly from looking at this circle, we can understand that it will be vertically up from this C point. So at this point. So let's call this as D. Another possible value, because remember we are only talking about the magnitude of the tau x dash y dash, it will be just below this thing. So at the two opposite ends of a vertical diameter, we have the maximum possible magnitudes of the shear stress. Here we have the maximum possible magnitude and here we have the maximum possible magnitude. But herein lies a very, very subtle point. We have to appreciate the fact that when we were considering about the principal stresses, so when we were considering about those principal stresses and we found out these two possible values of the principal stress angles, we had very nicely emphasized that when you are sitting at A and B, the values of the shear stress is equal to 0. However, now when we are sitting at D and at E, where we have the maximum possible value of the shear stress, we do not, please mark my words, we do not have 0 values of the normal stress. Why not? Because when you are sitting here, of course you are sitting at the maximum possible value of the shear stress, but you see what is the value of the normal stress here? It is certainly not 0. That would have been here, that would have been at the origin. We are not sitting at the origin. So this one has the abscissa value, the x coordinate value as this sigma average. Okay. So what we can mark this point as is tau x dash y dash max comma, sorry, it should be the other way around. So these are the coordinate values of the point D. Similarly here you will have the negative counterpart of it. More importantly, at E also you will have the abscissa value as sigma average. Now just as we had done this exercise where we were able to find out the angles pertaining to the principal stresses, can we perhaps do or proceed with a similar sort of strategy to find out the values of the shear stresses? So what could be the possible strategy? So let us take a direct inspiration from whatever we did earlier. So to recap very briefly, when we were considering the case of principal stresses, what we did was we did not consider the expression the expression number 3 or the equation number 3, rather we considered the other equation which was for the shear stress. Now we are interested in finding out the maximum value of the shear stress. So in a similar fashion, we should not be looking at the equation for the shear stress, rather we should be looking at the other equation, that is the equation for the normal stress, which means that we should be looking at equation number 3. So let us get back to that equation and try to find out what are the angles that pertain to the maximum possible values of the shear stresses. When tau x dash y dash is having the maximum magnitude, then we have already noted that the value of the sigma x dash should be equal to sigma average. Let us use that information by substituting it in equation number 3. All right. So we'll use equation number 3. I have basically rewritten equation number 3 here. All that I have to do here is to substitute the sigma average on this left hand side. You quickly note that sigma average is nothing but sigma xx plus sigma yy by 2, and that is nothing but this first term on the right hand side. So this entire thing, this is equal to sigma average. So on the left hand side you have sigma average, on the right hand side you have sigma average as the first term. Both of them cancel. So if we proceed after cancelling, what are we going to obtain? So we proceed from that right hand side of the chalkboard, and we cancel the sigma average and the sigma average from the left hand side and the right hand side, and simplify that in terms of we divide by cos 2 theta also. So we obtain tan 2 theta, maybe I will borrow a little space from here. So this tan 2 theta will be equal to minus all right. So we have this new expression for tan 2 theta, but again you note this is not some general theta, this is that theta which is corresponding to the maximum possible magnitude of the shear stress. So perhaps we should name this theta also in a particular way. So earlier we had used the subscript P to refer to the principal stresses, here we will use the subscript S for maximum shear stress. Okay. Now you see, whatever we are going to discuss from now on, as far as this is concerned, it will be exactly like the tan 2 theta p case. There also we had found out that tan 2 theta p is equal to something, and if that something has a particular numerical value, then we have two possibilities of the theta p. In exactly the same fashion, when we are solving a particular problem, these values, this will have some particular value, and correspondingly we will end up with two possible values of the theta s. So both of them are valid solutions. Now exactly analogous to what we had discussed earlier, it was actually imperative for us that we obtain these two values. Why? Because you see, whenever we are talking physically in terms of the requirement of the maximum shear stress, we end up from this diagram at two possibilities, this D and this E. So the angles that we are obtaining should also be referring to two possible solutions. Now can we look at this diagram and see what is that? Well, the answer is quite simple, that I need not unnecessarily clutter this diagram by drawing the white square, the white straight square. If I have this kind of a figure and I am saying that on this figure the value of the shear stress that I obtain is the maximum shear stress, this one, then I must necessarily have a complementary shear which is present on the top surface, which is like this. And of course, to complete the entire diagram, I need these also. So the answer that we will obtain as far as the maximum shear stress requirement is there, we will obtain this and this. Okay. Now can we perhaps obtain a few more insights from all these things? First of all, yes, the expressions of the normal stresses. The non-zero values of the yes, so we have Professor Gautam Chakraborty sitting here. So he has suggested that although I have not depicted a number of things here, but in order to avoid any sort of confusion, I should be depicting that we definitely have these things. So it should not occur to our mind that when we have these maximum values of the shear stresses, these normal stresses are absent. It is not at all true. As we can see here, this is the sigma average value. Okay. Now going forward, can we perhaps extract a few more pieces of insightful information from this diagram? The first thing that we want to find out, or we want to talk about, is that you see, when we are sitting at various different points, not necessarily at the points which pertain to the principal stress or which pertain to the maximum shear stress, any general point, what do they represent? They represent the values of the stresses that will be possible as we keep on rotating our little stress element. So, these are all the various possibilities. What do they correspond to in terms of the discussions that we had yesterday? They correspond to various different choices of our x dash y dash axis. Alright. Now, we are absolutely free to choose those x dash y dash axis. If we keep on increasing the value of the theta, we will get different values of this sigma x dash and the tau x dash y dash. Now, certainly the values are changing as we move along this thing, but no matter what you do, this is very much a circle. It remains a circle. No matter where you are sitting, it is a circle. It is obvious. It is almost trivial to note it, but it is not so trivial to note that no matter what value of the theta you are considering, it must be absolutely true that your radius is not changing, which means if we look at the expression of the radius, so we erase all of this thing. R is constant, of course. R is equal to this thing. Now, you see, when I am sitting at different points on this, I am actually obtaining various values of the sigma x dash, tau x dash y dash. Correspondingly, I will have some value of the sigma y dash also. If I substitute all those values there, sitting at any arbitrary point on this circle, it must be true that this R does not change. What does that mean? It means that no matter what the state of stress may be represented by in terms of my mathematical machinery, this R is an invariant value. I repeat, no matter what the particular combination of sigma xx, sigma yy, the tau xy may be, as I am sitting at or as I am sitting at different points of this circle, this R is an invariant value. Now remember, at one point in yesterday's lecture, I had mentioned one particular point. I had mentioned this important fact that sigma xx plus sigma yy is an invariant. Why is this an invariant? Because if you just refer to somewhere near the end of yesterday's lecture, as Professor Manasla had pointed out yesterday, that if we sum up equation number 3 and equation number 5, what we obtain is this thing. And please note that this does not at all depend on the value of theta. No matter what value of theta you take, this thing is going to be true, which means that this is like an universal truth. So, what is very important to note is that in the rich literature of mechanics of materials or mechanics of solids, this particular combination of sigma xx plus sigma yy, especially when we are talking in terms of 2D stresses, this will be referred to as the first invariant of stress. This is the first invariant of stress. You can as well say that this is the first invariant of stress, because the result is absolutely the same. Now, it is a very big temptation for us to say that then what kind of invariant is this? Well, in the traditional literature of mechanics of materials and mechanics of solids, the second invariant is actually something else, which I'll just quickly note down. This particular combination that we have, again this will turn out to be an invariant value no matter what combinations of sigma xx, sigma yy and tau xy you are taking. Alright. Now the question is it perhaps possible to express this R somehow by combining this first invariant of stress and this second invariant of stress? So this is my little exercise to you. So, please note it down. Express R in terms of the first and the second invariants of stress. This is basically an algebra problem that I am giving to you. Okay, this is not part of the tutorial sheet. This is something extra that we are discussing. We are going to, go for a little break. But before that, I will like to part with one discussion. You see, we have been talking about the radius as an essential requirement of the radius is that it should be an invariant, because of course it has to be a constant. If we are talking about the definition of this circle, in addition to the radius, it must also be true that no matter where you are sitting on this on the periphery of this circle, this center of the circle is also not moving around. It certainly cannot. It's almost trivial to say that. Okay, but if that is so, then this center must also be an invariant, and you see that this actually is true, because this sigma average is actually sigma xx plus sigma yy by 2. You just quickly note here, sigma xx plus sigma yy is itself the first invariant of stress. So definitely half of sigma xx plus sigma yy is also an invariant. So it is absolutely true that the radius is an invariant of stress, and the center is actually also an invariant of the stress. So everything makes sense here. So after the break, what we are going to do is obtain some useful expressions of the maximum values or the principal values of the stresses and the maximum value of the shear stress, and we'll see what we can go on from there. Thank you.